In this lesson, what we want to be concerned with is the displacement of a rod when we consider it under an axial loading. And we're going to get a little bit deeper than we did before. So let me get us started by refreshing what we know in the simplest case. You take a cylindrical rod and we're going to pull on it. And so we consider a cylindrical rod which is cantilevered on a wall, and we pull on it in the x direction. We know from Hooke's law that in the linear region, stress is going to be equal to the elastic modulus of the material times the strain. And if we want to give this directions, we can say, well, this is the y direction, this will be the x direction. We're applying a force P in that x direction. And so this Hooke's law will become sigma x equals E times epsilon x. And so now let's replace what we know about these terms here. So sigma is equal to Px over the cross-sectional area of our rod. Epsilon in the x direction is going to be equal to delta x over the length of our rod. Our length of our rod looks like this. And so we can easily rearrange this, and we'll find that the deflection in the x direction is going to be equal to the load in the x direction times the length of the rod over EA. So this is the simplest case, and it just builds off of Hooke's law. And now, what you'll see here is that this is a linear relationship. We're in a linear elastic regime. There's a linear relationship between stress and strain, and therefore there's a linear relationship between displacement and each of the quantities on the right-hand side of this equation. And so this allows us to use what's known as the principle of superposition, which means we can kind of break up our rod into different segments, and we can add each segment up linearly. So let me show you what that looks like. So again, if we consider a cantilevered rod, but this time, let's have it change shape as we go along the x direction. And so again, we'll apply a load Px. And now we have a little bit of a more complicated scenario. Here will be length 1. Here's length 2. And here's length 3. And accordingly, these things change cross-sectional area as well. A1, A2, and A3. So the superposition principle says that because this is a linear relationship, we can treat each of these as a separate quantity, and if we add them up linearly, we can get the total deflection. And so what that means is that our total deflection is going to be the sum over all the little elements times the number of loads applied, P sub I, the length of each one, the elastic modulus of each one, and the cross-sectional area of each one. And so in this case we'd have three terms, one for the first element, one for the second, and one for the third. If we assume the modulus is the same, they're all feeling the same force, then this would look like d total is going to be equal to P sub x over E times L1 over A1 plus L2 over A2 plus L3 over A3. And so we're adding up each of the tiny displacements of each one of these to get the total displacement of the entire structure that's under this load here. And so what you can imagine is if this is true in the case of a discretized rod where we have three different segments, that if we had an infinite number of segments and each of them got infinitesimally small, this summation would approach an integral. And so let's look what this looks like. So we can consider a structure that looks like this. So now our shape is changing along the x-axis. And we can maybe pull with P1 over here and P2 over here. And what we can do is we can take a little slice of this and look at a differential element, some small element, dx. And that element is going to be located at a distance x from this load here. And we know that applying this force is going to cause a little bit of displacement here, some new length, d delta. And so this, if this has a original length L, what we can do is we can zoom into this section here, this green dx, which is going to be elongated by some small amount. So this green portion here is dx. This elongation here is going to be d delta. And pulling on it in this direction is going to be p as a function of x. And the same on the other side, since this is in equilibrium. And then we can just go back to Hooke's law and write that the stress, which is going to be a function of x now, is going to be equal to p sub x over a as a function of x, right? Because the load varies along the length, the cross-sectional area varies along the length, and our strain is going to be this d delta over dx. And using Hooke's law, right here we can put this all together and get that dx over ax is equal to e d delta by dx. And if we solve for dx, solve for d delta, we can get that d delta is just going to be equal to p, it's a function of x, over e a times dx. And now all we have to do is integrate this equation along the length of it, and we arrive at the total deflection of this rod, which would be equal to the integral from 0 to L of P over EA times dx. And so this looks more complicated, but what's important to realize is that these are all the same equation, really. This is all saying that the deflection is going to be your force times your length over your elastic modulus times your cross-sectional area. And what it's saying is we can break this rod up into discrete elements where something might vary, maybe the length, the modulus, and the area of those elements, and we can sum them all up. And we can sum them all up because of the law of superposition, which says this is a linear relationship, and so these can be added together in series. And then finally, as we know from our calculus courses, if we have a discrete sum of a certain number of elements here, if we make this sum over an infinitely large number of infinitely small elements, what we get is an integral. So this becomes, instead of being discretized, it becomes a continuous description of our displacement as we integrate over the length of our member and multiply by all the things that are varying along the x-axis, p, e, and a, and integrate over x. With the mechanics of deformable bodies, so far we've considered stress and strain to be kind of two separate ways to solve problems. When in fact the most powerful thing you'll take away from this course is that when we use these two concepts together simultaneously, we can solve more complex loading problems. And so, let me give you an example. So let's consider a structure that is stuck between a wall at the top and at the bottom. And so if we label this top part A, this bottom part B, and the center C, and if we have a load applied at the center, pulling down with a force P, and we want to know the stress within this object, we can start by using a sum of the forces to get our equilibrium equation. And so in this case here, because we're pulling down at a point P, and because it's bound at the top and at the bottom, there's going to be a reaction force at the top, F sub A. There's going to be a reaction force at the bottom, F sub B. And then there's going to be this negative force P pulling down. And that's all going to be equal to 0. And so if we're given a value for the load P that's applied at point C, then what we have is one equation with two unknowns. And we're stuck. And so this is what's known as a statically indeterminate problem. A statically indeterminate problem will occur whenever you have more supports than are necessary to maintain static equilibrium. Whenever you have more supports than necessary to maintain static equilibrium, what you end up with is more unknowns, in this case 2, than you have equilibrium equations. In this case, we just simply have 1. And so whenever you have a statically indeterminate problem, we're lacking an equation to get at our unknown variables, in this case our unknown reaction forces. And so we need to know something else. And this is where we start to combine concepts of, say, equilibrium and stress, and our concepts of strain and displacement. In this case, what we know is that the total displacement of this object, A delta AB, has to equal 0. It's stuck at the top and it's stuck at the bottom, so this thing can't displace, and so the deflection of AB has to be 0. And so if we split this up and label a length AC from the top to the center, and a length BC from the bottom to the center, then using the principle of superposition, we can break up this total displacement into a displacement of the top part and a displacement of the bottom part. And so we can say, well, if this is true, then the displacement of AC plus the displacement of BC has to equal 0. And now what we can do is we can write these displacements in terms of these reaction forces and these lengths. And so we know that, if we recall, that delta equals some force P times the length over our modulus and our cross-sectional area, then we can write this as the force at A times the length of AC over EA plus the force at B times the length of BC over EA equals 0. And so now what we have is an equation that relates the forces here to some unknown. So we could, if we want, solve this and say the force so now we have a relationship between these reaction forces and the size and material properties of the rod. And so now we can go back to our free body diagram and learn something about the relationship between the load and the reaction forces. And so if we take this structure and we cut it here, what we find, and we redraw it over here, is that if we have a force A here and a force A here, and we can redraw our second part, the bottom portion, as C and B. We know that there's going to be a force B here and a force, the reaction force B here. And what this leads to is our ability to write these reaction forces in terms of the applied load P. And so what we end up with, after all this, is that the reaction force at A, F sub A, is going to be equal to P times the LBC over L, and our reaction force at B is going to be equal to P times L AC over L.